a batch of training samples. To accelerate SGD, we may want to use the computing power of distributed systems and split the training samples to multiple workers. So typically, in synchronized data parallelism for SGD, the training happens like this. First, the training data is split to n subsets. And we also have n workers. Each worker has a model replica or model copy. And when the training starts, each worker will pull the parameters from the shared parameter server and to update, to train each model replica using its training data subset. And after the training, the gradients from each worker will be updated to the shared parameter server to update the parameters. In large-scale distributed deep learning, we have a very large N. When we have a larger N, which is the number of workers, the computing time decreases. However, since we have more workers, the communication time, we have more workers to communicate with, so we have the communication time increases. So in very large-scale deep neural network training setting, in distributed systems, the communication time is the bottleneck. This work focuses on the quantization of the gradients to reduce the communication of gradients so we can get a better scalability in large-scale distributed training systems. Specifically, we quantize the gradients to only 3 levels without losing any accuracy. In the previous slides, the communication from the server to the worker is still the floating weights, and the gradient quantization cannot reduce the communication from server to worker. So we use a slightly different setting. Instead of pull the parameters from the parameter server, we just pull the averaged gradient. Since the gradient is already quantized one, in this way, we can reduce the communication in both directions, from worker to server and from server to worker. Our approach is motivated by the idea of stochastic gradient descent result bias. In supervised learning, the target function that we want to minimize is the training data loss over all the training samples. And this is how batch gradient descent update the parameters. Here, n is the number of training samples. Usually, it's very large, so the computation is very costly. A more feasible way is we randomly draw a sample from the training data set and use the sample gradient to estimate the original batch gradient, which is SGD. And in SGD, the expectation of the stochastic gradient is just the original batch gradient. So SGD is an unbiased gradient approximation approach. And the variance in the SGD even improve the convergence of for non-convex optimization. And in neural networks, you usually get a better generalization result. If so, why don't we just randomly ternarize the stochastic gradient, but keep the expectation of the ternary gradients just as the original floating gradient, so we can still get an unbiased gradient approximation. TernGrad is simple. First, we just need to get the maximum norm of the gradients, which is the maximum absolute value of all gradients. And then we multiply them, and then we get the signs of all gradients, so we can keep the directions of the gradient. And finally, we multiply them with the Bernoulli distribution, which is either 1 or 0. For each gradient, the probability of being 1 is the magnitude of the specific gradient over the maximum norm. Right side is a simple example. GT is the floating gradient, and ST is the maximum norm, which is 1.2. and we get the sums of all gradients, 1, -1, and 1. And we also need the Bernoulli distribution, and for each gradient, for example, for the first gradient, the probability of being 1 is 0.3 over maximum norm. And finally, we draw from the Bernoulli distribution to get a sequence of either 0 and 1. And finally, multiply all of them to get a quantized gradient. And we just need to communicate the ternary gradients and with one extra floating gradient. So we can significantly reduce the communication. If you do some math, the expectation of the ternary gradient is just the original expectation of the floating gradient. So it's an unbiased approximation approach. We proved the convergence under some assumptions. For standard SGD, it almost truly converges under some assumptions. We use almost the similar assumptions, but we do need a slightly different assumption 3, which is assumption on the bound on gradient. And on the 3 assumptions, TernGrad converges with the probability of 1. Here is the difference of the assumption for gradient bound in standard SGD and TernGrad. Since the maximum norm is always larger or equal to any gradient component, so indeed, TernGrad have a stronger gradient bound. However, we propose the 2 techniques to push the gradient bound of TernGrad closer to the bound of standard SGD. First, layer-wise Ternarizing. Instead of collect all gradients in the deep neural networks and ternarize them, we just simply do it layer by layer. Second, gradient clipping. This is different from the one in RNN. In gradient clipping, when the magnitude of the gradient is larger than some standard deviation, we just clip them. Experiment. In all our experiment, all hyperparameters are tuned specifically for a standard floating gradient descent and just fixed in TernGrad. This is initial experiments on MNIST. Y-axis is the accuracy, x-axis is the number for worker. As you can see, the accuracy are almost the same. Sometimes better, sometimes worse, but just within a small range of randomness because of the randomness in TernGrad. We also did experiments on CEPHA-10 and using Adam. The average loss is controlled within 1%. Again, since if we can also tune the hyperparameters specifically for like TernGrad, we should be able to reduce the accuracy difference. Applying TernGrad to larger dataset like ImageNet, we do need to tune some hyperparameters. First, since there is randomness in the TernGrad, we should reduce the randomness in dropout. Second, since randomness is a sort of type of regularization, sometimes we may use a smaller weight decay, but we don't add any new hyperparameters to tune. Here is the experiments on ImageNet for AlexNet. Without using gradient clipping to reduce the variance, we do have a 3% accuracy loss. However, TernGrad using gradient clipping, there is low accuracy loss. In all our experiment in this table, we don't observe any notable accuracy differences. More interesting, we found that when the batch size is very large, standard SGD have a smaller accuracy loss. However, TernGrad doesn't have it. Why? Kiskar explained that when the batch size is very large, standard SGD is easily to be stuck in sharp local minima, which have bad generalization. However, the noise in the TernGrad encourages space exploration to help to escape from those sharp local minima. Here is the convergence curve of TernGrad comparing with baseline, which is floating gradient descent. For both top one accuracy and training loss, the convergence curves matches well with each other. We also did an experiment on GoogleNet. On average, the accuracy loss is less than 2%. Again, all hyperparameters except the weight decay and the dropout ratio are tuned by Google for the floating gradient descent. We just fixed them. If we could also tune those hyperparameters, we should be able to reduce the accuracy difference. Finally, we proposed a performance model to estimate the speed up of TernGrad. In the figure, solid bars are for standard SGD, and shaded bars are for TernGrad. As you can see, TernGrad can always give a good speed up. In summary, when the communication over the computation, the ratio is larger, then TernGrad should give a better speed up. For example, if we have more workers to communicate, and if we use a smaller communication bandwidth, like if we use a low-speed Ethernet. And finally, TernGrad can also give a better speed up for new networks, like have more fully connected layers, like VGGNet versus GoogleNet. Okay. Conclusion. We proposed the TernGrad to reduce the communication in distributed training system to speed up the training. TernGrad can train from scratch and converges with the same epochs using the same learning rate policy. And it's very easy to be implemented. Our source code is online. And also there is some great work in NIPS here. And Dan proposed the QSGD, which solves similar problems. And if you have more questions, you may come to our poster, and I'd like to take questions, if any. Thank you.
If there's any question, please come to the microphone. There are 2 of them in the hall. If there's none, then I'll ask a question. So one potential application other than the distributed setting I can see is that maybe this kind of ternary representation of the gradient may be useful for some kind of, let's say, specialized hardware design. Is there any kind of, have you considered any kind of possibility in that direction?
Yeah, you mean use it for specific hardware?
Yes, building the hardware that's going to not require the full floating point precision, but just using the 3 bits, 3 or less than 2 bits.
Yeah, I think this is possible. And I see some framework also provide low precision gradient to reduce the precision of gradient. And our approach is a general solution, I guess. Yeah, if we also can get more information about the hardware, the communication bottleneck of the hardware, and we can customize our approach to specific hardwares. Yes.
All right, let's thank the speaker again.
Thank you.
So next up is Elad Hofer. He's going to tell us about how to close the generalization gap in large mini-batch training.
Okay, so hi everyone, thanks for inviting me. I'm Elad Hofer. This work is called Train Longer, Generalize Better, Closing the Generalization Gap in Large Batch Training of Neural Networks. This is joint work with Itai Khubara and Daniel Sudri, and we're all from Technion in Israel. So over the past years, we've seen an exponential growth in computational power and amounts of data available. In order to build larger and better models, we need to leverage this growth and ensure this compute power will be properly utilized. To utilize our hardware, we need to parallelize using bigger GPUs with many units and over many devices. For example, we can split our model between devices, also known as model parallelism. In fact, this was a key component in the seminal deep learning breakthrough by Krzyzewski et al. 5 years ago. However, this approach is hard to scale due to increasing costs of communication bandwidth. A simpler and perhaps more scalable way is to use data parallelism. Neural networks are commonly trained using stochastic gradient descent, or one of its variants, in which the parameter vector W is incremented by averaging the per-sample loss gradients across many batches. Since each gradient in the mini-batch is calculated independently using the same weight vector, this computation can be easily distributed between workers. Therefore, by increasing the batch size, we have the potential to improve parallelization and perhaps the training speed of neural networks. However, it was noticed by practitioners over the years that using large batches of samples caused a degradation in the generalization of the final models. We examined this phenomena in a common and widely used resonant model trained with momentum SGD over CIFAR10 dataset. As can be seen in the figure, during training, validation error seems to plateau near similar values for different batch sizes. And it is not clear why is there a large difference in the generalization error when the learning rate is decreased. This was further highlighted by Kaskar et al. Last year, who noted that this generalization gap might be an inherent problem with large batch training, and that it persisted in models even when trained without any budgets or limits until the loss function ceased to improve. It was suggested that this is related to small batch update being more noisy, which helps avoiding sharp local minima and reach flat minima, which have better generalization. Since validation error plateaued and training error decays near zero, we searched for another state variable to inform us of the learning dynamics. We measured the distance traversed by weights over the course of training and found slight variation between batch sizes. Interestingly, a small batch training reached a significantly larger distance from initialization compared to large batch. For example, a batch size of 64 reached a distance almost 4 times larger than the distance reached with a batch of 2048. Since the curves for the different batch sizes seem to have a suspiciously similar shape, we changed the x-axis from epochs, the number of passes over the data, to the number of SGD iterations. This caused an approximate data collapse, where all the curves fell nearly on top of each other, revealing a universal logarithmic curve. As we explain next, this observation helped us close the generalization gap. Later, we will also address the origin of this logarithmic behavior. Next, we describe our experiments aiming to close the generalization gap. We performed our experiments using ordinary momentum SGD, as it usually exhibits better generalization than adaptive methods such as ADAM. Additionally, we used gradient clipping to avoid numerical stability. As the gradients are highest during the early steps of training, its effects are very similar to warm-up, decreasing in the learning rate during these first few steps of training. As mentioned before, there is a noticeable generalization gap between small and large batch size. For example, examining ResNet 44 over CIFAR10 dataset, we see degradation of over 6% in final validation accuracy. Our first step is to adapt our learning rate so that batch statistics will stay similar to small batch regime. We find that for our test case, a square root scale is appropriate so that the variance of weight update will stay approximately the same across batch sizes. This can change depending on ratio of the mean and variance of the stochastic gradient in the dataset. Gradient clipping ensures this scaling will not cause divergence in early steps of training. Making this adaptation, the validation accuracy improves considerably, but the gap remains. Next, we also use what we call a ghost batch norm, where instead of computing batch normalization for a complete batch, we split the batch into several smaller slices and compute batch norm for each one independently. This further helps to mimic the statistics of each one of the slices with as small as needed batch size. Ghost batch norm adds no overhead to training process and has the nice property that it can be done over each slice on different device with no added communication. This further increases final validation accuracy with a still apparent gap. Using these modifications, we found that now the distance from initialization is better matched across batch sizes. However, as the graph indicates, small batch training still reached a significantly larger distance compared to large batch. This indicates that insufficient number of steps is performed with large batches. This is not surprising, since as the batch size increases, there is a decrease in the number of weight update iterations per epoch. According to this observation, we adapt the training regime so that in all batch sizes we'll perform the same number of steps. In short, we train our model a longer number of epochs in each training phase. In this graph, you can see that for a large batch training regime, this causes a large number of iterations in what seems to be a plateau region of a validation error. As we hoped for, this completely closes the generalization gap, and we now find that large batches can generalize as good and even better than small batches. For example, as you can see in this figure, a batch of 4096 with an adapted regime reached a better validation accuracy than the same model with a small batch of 128. We confirmed this finding for numerous datasets and models and find a similar effect, that when the number of iterations is fixed for all batch sizes, there is no apparent generalization gap. For example, we were able to train on ImageNet using the AlexNet architecture with a batch size 64 times larger, with better accuracy than the original, with small batch result. One key question is why weight distances increase logarithmically. We suggest an hypothesis based on a physical property, that during early phase of training, that is, when the training error is still high, we traverse a noisy landscape with noisy step approximations. This is known as random walk over random potential, where the landscape is modeled to have noise proportional to the gamma power of traverse distance. This phenomena is known to cause an ultra-slow diffusion, as described by Marineri over 3 decades ago. The weights are moving from their initial point at logarithmic rate of power gamma. Recall, we previously found similar behavior with gamma equal to 1. We then measured the standard deviation of training loss and estimated gamma. As predicted by the model, we found that gamma was indeed equal to 1. An informal explanation for this behavior can be visualized, in which for the particle to move a distance d, it has to pass a potential barrier of height d power of gamma. This requires an exponential time to reach a desired goal. Therefore, the distance d traversed is logarithmic in time. So, we consider this behavior as a possible explanation for the need for many gradient updates. An exponential number of iterations is needed to reach areas that yield good generalization. To summarize our findings so far, in contrast to previous works, we observed that there is no inherent generalization problem when training with large batch. All that is needed is to adapt the training regime in order to achieve comparable and even better generalization. We suggest an explanation for this mechanism, for the mechanism behind this phenomena, a random walk over random potential, requiring an exponential number of training iterations to reach a desired minimum. Additionally, it turns out that the total wall clock time required to train a model can be reduced in some cases. Since the time our paper went public, several works continue to make progress in training large models with larger batches using ideas very similar to ours. Experimenting with computational resources unavailable to us and more aggressive learning rate regimes proved to allow a dramatic wall clock decrement, with latest work allowing to train ImageNet models in as low as 15 minutes, which previously required several days to converge. Finally, we note another intriguing phenomenon. We appear to need many epochs to improve generalization in what may seem as an overfitting regime, where the training error and loss vanish, validation loss increases, and weight norm diverges. Early stopping practice suggests we should not do that we should stop training when the validation loss increases. And yet, the validation accuracy keeps improving, although very slowly. We show this to happen even for logistic regression over separable data, or in other words, a single-layer neural network with logistic loss. In this case, we prove that such behavior is related to the slow convergence to the maximum margin solution. This is also true for deep models under several strong assumptions. To learn more about this, you are invited to read our recent work, The Implicit Bias of Gradient Descent on Separable Data, by Daniel Sudri, myself, and Nati Sribro. So that's all. Thank you very much for your time. You are invited to our poster, and there's also a workshop on Saturday.
So same thing, if you have questions, please come up to the microphone. So if not, so the interesting thing I see is that you see that given a model, the same number of parameters, now you can close the generalization gap when using the large mini-batch. But is there any kind of relationship between the size of the mini-batch that is required or that is necessary versus the size of the model itself? Is it possible that if we just increase the size of the network or the number of parameters much larger, then we can actually work with the large mini-batch and it has the same effect of having a small mini-batch only?
So we can find we can get actually the same accuracy in any batch size. I think one main point is that currently we have certain computational sweet spot for batch sizes and size of models and our current hardware. But as we will grow in computational power, we can try and get larger and larger batches to converge with even larger models.
Thank you. Let's think. Oh, there's a question.
Here. Have you tried large batch training on recurrent nets?
So we have some preliminary results.
What did you see there?
It's possible to train even recurrent networks with as large as you want batch size. We have some preliminary results, and we'll hope to publish them.
Okay.
All right, let's thank the speaker again. So our next speaker is the Tom Rockstashel, and he's going to tell us about how to prove a theorem in an end-to-end differentiable manner.
Hey, hi there. It's absolutely fantastic to be here. My name is Tim Rockstashel. I'm a postdoc at University of Oxford, and this is joint work with my former PhD advisor, Sebastian Riedel from University College London. And this work is really in the intersection of deep learning and symbolic reasoning. So, you're in the NIPS 2017 Deep Alchemy session, so you should all be, I guess, excited about neural networks. And there are things, there are properties that are exciting. We can train them end-to-end from input-output data. They achieve very strong generalization. But at the same time, they also need a ton of training data, and generally they're not interpretable. And this is a bit ironic because if we go back a few decades, then when we talked about AI, then we meant mostly first-order logic-based expert systems. And despite the fact that we had to define rules manually and there was no generalization beyond the rules that we defined manually, these systems didn't need any training data and they were interpretable. So we could go to some domain expert, show the rules that we came up, and ask them to look over these, add some rules, fix certain rules. So these are nice properties. So how can we get the best of these two worlds? So particularly our aim is to build a neural network for proving queries to a knowledge base. So that means the proof success will be differentiable with respect to vector representations of symbols. And that allows us to actually learn these vector representations end-to-end from the proof success. And it also allows us to make use of provided rules in soft proofs. And most importantly, it will allow us to induce interpretable rules end-to-end from the proof success. Now, at this point, I need to mention that the combination of machine learning and logic has a long tradition. There was a very nice keynote talk this morning. There's work on fuzzy logic, there's work on probabilistic logic programming, on inductive logic programming, as well as neural symbolic connectionism. What we contribute is a model where we make sure that we learn vector representations of symbols and we learn them end-to-end from the proof success. So this is our contribution in this mix of, I guess, combinations of machine learning and logic. So how do we go about this? Well, I think Nando summarized this very nicely in a tweet last year. So you neuralize things, right? That means you implement a known thing with deep nets. So you neuralize this, you neuralize that, and then you train it. So great. Then Jan LeCun remarked, well, this is sort of like kernelized used to be. So we thought, well, obviously we can combine the two. So let's neuralize Prolog's backward chaining algorithm using a radial basis function kernel for unifying vector representations of symbols instead of doing symbolic comparison. And I'll talk about each of these in the next slides. Okay, so what's Prolog's backward chaining algorithm? Well, let's assume we have a knowledge base like the one on the left. So we know that Abe is the father of Homer, and we know that Homer is a parent of Bart. Also, we have this very interesting knowledge that a grandfather is a father of a parent. So now we can get a query such as, is Abe the grandfather of Bart? And on a high level, what backward chaining is doing, it's translating this query into other subqueries using rules. So in this case, we would translate this query into two queries, namely, is Abe the father of some Z, and is that Z some parent of Bart? Now, backward chaining is going to do this for every, is going to attempt this for every rule in the knowledge base, and thereby specifying a depth-first search. There's one very central operation in backward chaining, which is called unification. So assume that we have this query, is Abe the grandfather of Bart? We're going to try to unify this with the first rule in the knowledge base. So note here that a fact is also called a rule without a body. So what unification is going to do is going to basically check for pairwise symbol equality. So at this point, we get already a failure when we try to match grandfather off with father off because they're just two different symbols. So assuming that we have some upstream proof state where our proof so far has been successful, now we will have a failure. Right? So the same happens when we try to unify with the second rule in the knowledge base. Because again, grandfather off and parent off, they're two different symbols, they won't match, and we get a failure. In the third case, something interesting happens. So now we actually have a unification success. Because grandfather matches grandfather, and for the free variables in the rule, we actually create variable bindings. So we're going to bind X to Abe, and we're going to bind Y to Bart, and we have a new downstream proof state that is successful and where we carry around these bindings for then further proving subqueries. But here is an instance where something annoying happens. So we are querying for grandpa of Abe Bart, and it's going to fail because, again, grandpa off and grandfather off, they're going to mismatch. Right? So the downstream proof state is going to be a failure, and our idea is quite simple. We say, well, wouldn't it be nice if we could learn vector representations of these symbols and do this comparison in a vector space? So at this point, our proof state is not just a success or a failure, but it's some continuous score between 0 and 1. And when we compare grandpa off with grandfather off, we take the vector representations of the two, and we use a radial basis function kernel to measure their similarity in a vector space. We're also going to combine that with the upstream proof success. So let's assume this is 1 so far. So now we get the minimum of 1 and whatever score we get from the similarity of grandpa off and grandfather off. So this gives us a new downstream proof state where we still have this variable binding, so we keep that symbolic, but we also have this little neural network that can give us a continuous score between 0 and 1 for the unification. Okay, so now let me give you a full example. We start with a proof state of no variable bindings and a score of 1. We have the query, is Abe the grandpa of Bart? And we're going to match that with we're going to unify that with the first rule in our knowledge base. This doesn't create any new variable bindings because there are no free variables in our rule. However, we get this neural network that basically measures how similar is grandpa off to father off, how similar is Abe to Abe, and how similar is Homer to Bart. Something similar happens for the second rule, and for the third rule, we get this interesting behavior where we now have to recurse. So we create these variable bindings for X to Abe and Y to Bart. We have this little neural network that compares grandpa off with grandfather off, and we have two subqueries that we still have to prove. So the first one is Abe indeed a father of some Z? So we recurse. In this case, let's say, try to apply the third rule first. We have a very simple heuristic that avoids cycles by just making sure that we never apply the same non-ground rule twice. But for this unification with the first rule, we get this new proof state where we unified father of Abe with Abe, and Z with Homer. That means we created a variable binding of Z to Homer. We have a slightly larger neural network because of these these similarity calculations in vector space for the symbols that we compared. And we still have one subquery that we have to prove. We now have to show that Homer is indeed a parent of Bart. we're again going to apply recursively all the rules. Same happens for this other branch of proving, and at this stage we have leaf nodes. So we have 4 leaf nodes at the bottom, also 2 leaf nodes in this tree at the top. And I'll show you in a second how we then build a training objective such that we can train this model end-to-end and backpropagate through this proof. But there's one interesting thing that I want to emphasize here, and that's the following. Let's assume we don't know this rule. Right? We don't have this grandfather of rule, but we might have some inductive bias that says, well, we assume that in our knowledge base it would be useful to have a certain transitivity rule between unknown predicates that would help us prove statements in this knowledge base, or queries to this knowledge base. And the funny bit is that we can actually just use a parameterized rule where we have these unknown predicates, and we can learn the vector representations of these unknown predicates like any other vector representations of symbols in our knowledge base. So the algorithm doesn't change, the computation graph doesn't really change, but we can now learn these unknown predicate representations and thereby induce logical rules using gradient descent. Okay, so given these leaf nodes in the graph that I showed, each of these represents a possible proof. Each of them has a set of variable bindings and also has this neural network that evaluates to a score between 0 and 1. So we then use a max pooling operation to actually get a probability of proving this query condition on the knowledge base and the parameters of the model. We can then use that in a negative log likelihood loss with respect to some target proof success and train it end-to-end using stochastic gradient descent. So that means the vectors that we learn, they are learned such that the proof success is high for some known facts and it will be low for some sampled on negative facts. So we compared this against Complex, which is a state-of-the-art neural link prediction model that was shown to outperform other neural link prediction models such as Transy and Howley and Distmalt on large-scale knowledge bases. Here we test this on 4 benchmark knowledge bases that are medium-sized. And we compare this against our approach, and first we noted that that doesn't really give us much. So we are on par on nations and UMLS, but on countries and kinship we get mixed results. It's important to note at this point that we still gain something because we can, after training, we can look at the induced rules. So it's still nice, but we were a bit disappointed. So we've stepped back and thought about, okay, there seems to be something inherently difficult in training this end-to-end differentiable prover. So we came up with a auxiliary task where we basically try to make sure that the vector representations of symbols that we learn are close to the ones that Complex would learn. And at test time, we still just use our end-to-end differentiable prover. So it's this regularized prover that actually pushed us above the bar on most of these knowledge bases. But again, it's mostly important that we can afterwards look at induced rules. So this is really was our main motivation. So here are a few example rules. So these are transitivity rules. The first one would, for instance, state that if a place is in some subregion and that subregion is in a region, then that place is in the region. Or likewise, the second one would say if some entity 1 interacts with some entity 2, and that entity 2 interacts with some entity 3, then the entity 1 interacts with entity 3. So to summarize, we used Prolog's backward chaining algorithm as a recipe for recursively constructing a neural network to prove queries to a knowledge base. And thereby the proof success is differentiable with respect to vector representations of symbols in the knowledge base, and it allows us to learn these from data using gradient descent. But most importantly, it also allowed us to induce interpretable rules from data via gradient descent. There were various computational optimizations that we had to apply, so we had to make sure to actually batch proof lots of queries at the same time on a GPU. We also had to come up with some dynamic tree pruning. I didn't talk about these in the talk, but if you're interested in these, please come to our poster. And for future research, we are very keen to scale this up to even larger knowledge bases. Also, we are very interested in connecting these models to recurrent neural networks that encode natural language statements, such that maybe at some point we can prove with natural language for question answering. Thank you so much for your attention.
Question? Yes.
Thank you for the exciting talk. How do you handle negation? Or do you?
Second, how we do negation?
Yeah.
We don't have any. We don't support any negation right now. It's a simple answer, but.
There's another question.
How big do the networks generated by this method tend to be?
So they tend to become very big very quickly, right? We get this exponential blow up basically in terms of the tree depth. So we have to constrain the tree depth. This is a hyperparameter we use, and we are right now limited to these medium-sized knowledge bases. So the largest one is 50,000 facts.
So actually, that was exactly the question I wanted to ask. So the computational complexity is still the exponential with respect to the number of the rules or the knowledge triplets in the knowledge base, is it?
Yeah.
So then, so since you put it into the future direction, what's your plan on how to scale it up by, overcoming the barrier of the exponential?
Right. So I think it would be very exciting to think about how to apply, for instance, reinforcement learning in the setup, where we make some hard decisions in terms of which proofs to expand. There's actually quite exciting work in this direction now in automated knowledge-based completion. If you're interested in that, we have a workshop on Friday where I know there's a few papers who are actually exactly going in that direction. So I think it's a very exciting direction.
Thank you. Let's thank the speaker again. So now we switch our gears and then move on to the session on the generative adversarial net. And our first talk is by the Vaishnav Nagarajan on gradient descent GAN optimization is locally stable. All yours.
Okay. Good morning, everyone. Welcome to my talk on why gradient descent GAN optimization is locally stable. This is joint work with Zico Coulter. So this is going to be a rare deep learning talk where there are not going to be any experiments. So what we will try to do is to answer the call that Ali made yesterday, which is to understand optimization in deep networks. In particular, we've seen that GANs work really well, but we don't really know why they work well. And when you initially look at it, it doesn't really seem like the optimization should work well. So as we all know, GANs or generative adversarial networks are a breakthrough class of generative models that was introduced a couple of years ago. And they have been able to learn an underlying distribution over really complex data like images of celebrities. And they've been able to produce realistic samples drawn at random from this learned distribution. Now, while a lot of empirical work has gone into making GANs to work well on a variety of applications, there's very little or no theoretical understanding of why they work well. So in this work, we bridge this gap by studying a fundamental question about when and why will GAN optimization converge to a good solution. And to study this, we will use tools from nonlinear systems theory. Now, before I formally pose this question, here's a quick introduction to GANs. I'm sure many of you are already familiar with this. So GANs are made of two parameterized models, a generator and a discriminator. And the generator tries to generate random images from its parameterized distribution, and the discriminator tries to classify these generated images from images that are produced from the real world. Now, a GAN is cast as a game between the generator and the discriminator using a min-max objective, V, as shown here. This objective looks something like this, and it intuitively corresponds to the accuracy of the discriminator in its classification task. Now, naturally, we want the discriminator to maximize this objective, and we want the generator to minimize this objective. And the goal of GAN optimization is to find an equilibrium point of this game, or equivalently, a saddle point of this min-max objective. Now, for a given discriminator-generator architecture, there would be many different saddle points. Ideally, we would like to converge to the global equilibrium of this game. This is because this global equilibrium would correspond to a scenario where the generator distribution matches the real-world distribution, and that is ideally what we want from a generative model. But then this is a strong assumption that such a global equilibrium can even be realizable by the given representations of the generator and the discriminator. So, and we want to study whether, given such a global equilibrium, it has good convergence properties. But then this is a strong assumption, and in our paper, we also relax this to some extent. But what I want to highlight is that even if this is realizable, we do not know until now whether such an equilibrium point has good convergence properties. More precisely, here's the question we want to ask. Now, we know in practice that GAN optimization typically seems to find a good solution that corresponds to a global equilibrium. But there's only so much we can tell by looking at the images that are generated by GAN training, by a GAN after it's been stopped training at some point. But what we really want to know is whether it has converged to that global equilibrium, or at least it's headed towards convergence. What if in reality the system is simply very close to equilibrium but simply cycling around the equilibrium? Or even worse, what if there are these tiny bad regions near equilibrium, and if you allowed the system to train for a sufficiently long time, it might explore this bad space and diverge away from equilibrium? So in order to rule out such non-convergent dynamics, at least near the equilibrium, here's the question we want to pose formally. Is the equilibrium even locally exponentially stable? Informally, what this means is any initialization that is sufficiently close to equilibrium guaranteed to converge to that equilibrium under a given optimization procedure? As you can see, this is a very fundamental guarantee, or a minimum requirement, if you will, from that is desired of the optimization procedure for it to even make sense in the first place. And it's been an open question as to whether this holds good. And this is what we look at in our work. Now, before I get to how we answer this question, let me first convince you that proving GAN stability is actually non-trivial. So if we look at the objective near the equilibrium, it turns out that it is concave in terms of the maximization problem in the discriminator parameters. This is good for us. But unfortunately, the objective is also concave in terms of the generator parameters, even arbitrarily close to the equilibrium. Now, this is not simply because you're using a deep architecture. This is true even when you have a linear discriminator and a generator model. So there is a fundamental issue that seems to be there in the GAN objective itself. So in summary, what this means is we do not have a convex concave problem, in which case we would have had really nice guarantees, standard convergence guarantees. What we have is a concave-concave problem, and this does not have nice properties. In particular, if you look at the concave-concave problem, there are regions arbitrarily close to the equilibrium, where if you were to freeze the discriminator and update only the generator multiple times, you might simply diverge away from equilibrium because of the concavity. So in the context of this challenge, let's see how other concurrent works have tried to prove stability for GANs. Most of these works, in some sense or the other, consider an optimization procedure where the discriminator is trained more often than the generator. So what this does is it takes care of the fact that the generator updates are not as desirable as we want. Or in other words, since your discriminator is somewhat trained closer to optimality, what you have is a pure minimization problem without the issues of a min-max problem. Now, but then this does not really echo what we have done in practice, which is to update the discriminator and the generator at the same frequency alternatingly. And we know that even such an algorithm works. So how do we explain this? So let's consider the following GAN optimization problem, GAN optimization, where you, at each time step, update the generator and the discriminator simultaneously and infinitesimally. What this does is give us a time differential equation, or a nonlinear system. Now, this is, as you can see, is much closer to what is done in practice, where the updates on the discriminator and the generator are of the same frequency. Furthermore, it turns out that this is also even computationally cheaper, and therefore it's interesting to study this algorithm both from a theoretical, both due to theoretical reasons and computational reasons. Okay, so given this simultaneous gradient descent GAN optimization, here's our main result. What we show is that despite the concave-concave GAN objective, and despite not training the discriminator to optimality, that is, despite not training the discriminator more times than the generator in each iteration, surprisingly and fortunately, simultaneous gradient descent GAN equilibrium is actually locally exponentially stable under suitable conditions. That is, there are no non-convergent dynamics, at least near the equilibrium. So how do we prove this? Our main toolkit is nonlinear dynamical systems theory. We use different tools from nonlinear systems theory, but here's the most important theorem. What this theorem says is, take the Jacobian of the system, that is the gradient of the dynamics of the system with respect to its parameters, compute it at equilibrium, and see whether its eigenvalues have strictly negative real parts. If that is true, then what we have is that the equilibrium of the system is locally exponentially stable. So our goal here is to take the Jacobian of the GAN system, compute it at equilibrium, and show that this holds good under some conditions, despite the concave-concave objective. So in case you're curious, I will highlight some technical challenges that come up in this proof. OK, so let's look at the Jacobian of the system near the equilibrium. Now, in particular, I want you to focus on the lower diagonal block, which corresponds to the generator parameters. Now, it turns out that because of the concave-concave objective that I highlighted a couple of slides ago, this block could be positive semi-definite. What this means is that the whole system could potentially have eigenvalues with positive real parts, and the whole system could potentially be unstable. However, here's a key observation. It turns out that for the way that GANs are formulated, this block could be this block is a zero block. So this is better than having a strictly positive definite block. So what we have is a zero block at equilibrium, but this is still not the best situation. The best situation would have been when this block was a negative definite block. So the key challenge is still non-trivial, which is to show that the eigenvalues of the whole matrix have strictly negative real parts, despite this zero block along the diagonal. So how do we show this? Basically, we identify some strong curvature assumptions under which the rest of the matrix has some nice properties. And given these nice properties, we show that it's sufficient for these nice properties to hold good to show that the eigenvalues of the whole matrix have strictly negative real parts. So this completes our proof. OK, so now going back, let's look at the dynamics of a simple GAN system that learns a one-dimensional uniform distribution. The discriminator and the generator consist of only a single parameter each. As you can see, the dynamics of the system is quite nonlinear. But what we have from the theorem is that it still converges as long as the system has been initialized sufficiently close to the equilibrium. So there are no non-convergent dynamics near the equilibrium. OK. Finally, based on our analysis, what we also do is to propose a modification to the optimization procedure, and this provably enhances local stability for these systems. In particular, modification is that the generator should not only minimize the objective, but it should also minimize the norm of the objective's gradient with respect to the discriminator parameters. Now, this is not super intuitive at first sight, but we provide some intuition in our paper. But for example, you could think of this as a damping term in nonlinear systems terminology. But what I want to highlight is that this provably enhances local stability of these systems. So let's see an illustration. Now, if you look at the Wasserstein GAN under the simultaneous gradient descent updates, as shown on the left, note that this is not how you train Wasserstein GANs in practice, but under the simultaneous gradient descent updates, because the Wasserstein GAN objective breaks some of our strong curvature assumptions, what we have is a system that is not necessarily converged to the equilibrium, as you can see on the left. However, once we add our regularization term, the system is going to converge to the equilibrium in a local neighborhood around the equilibrium. OK, so this brings me to the end of the talk. What have we seen? We've seen that we can use nonlinear systems theory to prove local stability of GANs. Specifically, even though the GAN objective is concave-concave, what we know is that simultaneous gradient descent equilibrium is locally exponentially stable. And this is in line with the fact that GANs have worked very well empirically so far. And based on our analysis, we are also able to propose a regularization term that provably enhances local stability of these systems. Now, looking ahead, what do we have? So at a concrete level, there are many interesting questions. First, while our analysis is quite general, we still have not been able. We've not proved stability for many other objectives and variants of GAN optimization that exist in literature and that are being used. Furthermore, we make some strong assumptions, including the fact that the global equilibrium is realizable, and we would definitely want to extend this. We would definitely want to relax these assumptions further. And most importantly, we would also like to prove global convergence for GANs. Our results only imply local convergence. But we would want to prove global convergence, at least in the case where the discriminator and the generator are linear architectures. But at a high level, I would like to highlight two important points. First, there are many interesting and exciting theoretical questions in GANs, both from an optimization and a learning theoretic perspective. And in order to develop provably better and better GANs, it is crucial that we gain insights into these questions. And secondly, if you look at our paper, what it really is an application of nonlinear systems theory to understand a modern optimization problem, in particular a min-max optimization problem. And what we hope in the future is that we can use many other powerful tools that exist in nonlinear systems theory to understand many other kinds of complex optimization procedures that we use today, especially in the case of deep learning problems. So thank you, and if you have any questions, please feel free to ask me now or during the poster session this evening.
So if you have questions, again, there are 2 microphones standing. Please come. Is there a question or? Probably not. Okay. So then I'll ask a question here is that all this convergence analysis will assume that, okay, there is a point of convergence there, right? And then, like you were talking about, okay, so the GANs in practice are working. So how do we actually tell that those awesome GANs that can generate celebrity faces and so on have actually found the conversion point rather than, we just stop somewhere when we were expecting the samples and then, realize that, okay, they look good enough?
Yeah, okay, good question. So like I said, what our theory tells is that if a good equilibrium exists, and if you were sufficiently close to it, you would have converged to it. So what your question basically aligns with some of the future work that I highlighted, which is to first show global convergence, and next to identify the situations where the equilibrium even exists in the first place. But yeah, our results do not really tell us whether these systems have actually converged to the global equilibrium or not.
I see. All right, thank you. Yeah. There's a question.
Just one question. It's in stark contrast with the practical experience if you try to implement a GAN from scratch. So can you comment on you did on the last slide, but can you comment more precisely how to explain the practical experience? Is it not reaching this local attraction region, or is the assumptions justified that you're making? What really is in this gap between practical experience and your theory?
Okay, so yeah, so what we did observe in practice is that, especially even for the regularization term that we added, it enhances local stability, but we cannot really comment on the global behavior of our regularizer. And yeah, so these assumptions, okay, so the results that we have apply even in the case of deep learning systems, because in a local area around the equilibrium, even a deep network is going to be convex or concave. But yeah, our results don't really comment on how it extends to arbitrary regions that are far away from equilibrium. But our assumptions are still valid in that near the equilibrium things are going to be quite nice. Yeah.
All right, let's thank the speakers again. So we move on to the spotlight session. We have the 8 papers to be presented. It's going to be 5 minutes each, but there's not going to be a question, so please do check out their posters in the evening.
Okay. All right. Thank you very much. Good morning, everybody. So this is joint work with Zach Cranko, Aditya Menon, Lijian Q, and Bob Williamson. And if you look at essentially the previous paper and many other papers actually dealing with the dynamics in a general form of GANs, this is not what we're going to talk about. What we're going to talk about is essentially about the loss function that has been optimized in the min-max formulation of the GANs, and in particular in more recent papers than the seminal one from Goodfellow, which puts an very nice information theoretic layer on top of this game. And what we're going to do is actually we're going to put an information geometric layer on top of that one. So this kind of layered cake starts with, from the bottom, from this very nice loss introduced by Goodfellow et al. So you have a very abstract formulation of this loss, which is displayed on this slide. I'm not going to explain this, the loss, because actually it's kind of well known currently. The optimization of this loss, the minimization of this loss from the generator standpoint, and the generator parameter is actually theta displayed on the slide, is what I will call the f-GAN game of P and Q, where P is actually the distribution you want to model and Q is the distribution you learn throughout the fitting of parameter theta. So I will in particular essentially forget the parameter omega of the discriminator in this talk. So more recently, Novozin et al. In a very nice paper actually put an information theoretic layer on this f-GAN game and essentially proved that, of course, conditions apply, that the f-GAN game is up to some extent equivalent to an f-divergence between P and Q. So conditions apply, of course, if you get just a subset of these conditions, and essentially you end up with an inequality, and so on. But let's keep the equality for the sake of this talk. And it gives actually a very nice overview of the GAN game, because it says that if you solve the GAN game, so if you minimize efficiently from the generator standpoint this loss function, then essentially you're going to have a form of convergence in distribution between P and Q. So that's very nice. But actually, when you look at deep learning papers, people would typically use very complex architectures to model the generator full of parameters. So there is a question which is on top of this layer: what is happening for a parametric standpoint, and what kind of distribution, in fact, could you model with this kind of formulation of the GAN game, right? So you have, for those of you who might know this kind of very old theorem, you have a very known theorem which essentially tells you that if you take exponential families and you compute the KL divergence between two exponential families, modulo some assumptions, and essentially this is just going to be a Bregman divergence between their parametrization, right? So the question is, how can we go upstairs? Because essentially by sticking to exponential families, we stick to the KL divergence. So F equals KL, which is already different from the seminal choice of Goodfellow, which was essentially a Bose-Einstein entropy in this case. So what we did is we explored this additional layer we wanted to put and came up with a generalization of this old theorem, which essentially gives you that the f-GAN game is indeed equal to a geometric distortion between the parameters of your two distributions, P and Q, plus an additional penalty. So this simplifies for exponential families to this very old theorem. And actually, this generalization holds for a family of distribution which has received over the past 10 plus years some extensive treatment in differential information geometry and generalized thermostatistics. These are called deformed exponential families. You will see in this equation that the generator actually appears on the form of an escort distribution, which is a transformation of your distribution. And in the case of exponential families, actually, the function chi that you have here actually is the identity. So the escort is the distribution that's the same object. We also completed the information theoretic layer of the f-GAN paper, introducing essentially proper composite losses. And what we did then, the next question was essentially, since the generator appears on the form of an escort, can it be possible that actually deep architecture would model escort distributions? And actually, under some assumptions, it is actually the case. And what you can show is that deep architectures are actually very able to model some very complex factorization of escort distributions. And so what we obtain is actually a correspondence between all the parameters of the deformed exponential families and the parameters of the generator. So these depends on properties of the activation functions, and it turns out that they are exactly or approximately made by popular choices. And we have other results and, of course, some experiments, and you are very welcome to meet us at the poster, which is number 100. Thank you very much.
Hello, I'll be talking about the unsupervised image-to-image translation networks. This is Minyu Liu, joint work with Thomas Burrell, Yang Kaut. We are all from NVIDIA. So the problem is the image-to-image translation, where we want to learn an image translator that can translate an input image in one domain to a corresponding image in another domain. So usually the image translator is realized as a convolutional neural network, and we want to learn the parameters. So this problem can be studied in two settings, supervised or unsupervised. In the supervised setting, you have a data set where the images are given as a pair. For each input image, you know how they will be translated. In the unsupervised setting, you don't have the luxury. All you have are two data sets, one from each domain, and you have to figure out the translation unsupervisedly. In the unsupervised setting, it leads to a harder learning problem, but data set collection is easier because it doesn't need alignment. So from a probabilistic point of view, the unsupervised image-to-image translation problem is a problem of estimating the joint distribution of images in different domains by using samples from the marginal distributions. You have data images from PS1, data image from PS2, and you want to estimate PS1, S2. This is the EO-post problem, because a set of infinitely many joint distributions can be derived from two marginal distributions. In order to make progress, you need to make assumptions. You need to bring in the right inductive bias in the network design and objective functions. What we do is to make the shared latent space assumptions. We assume there's a shared latent space, and we have two encoding functions, E1 and E2. Given a pair of corresponding images in two domains, we can use E1 and E2 to map them to the same latent code. We also assume we have a pair of generation functions, G1 and G2. Given a latent code, we can map them to a pair of corresponding images. If we can learn E1, E2, G1, G2 from training data, then we can achieve image translation. We don't have a pair of corresponding images to the training data set, but we can use E1 and G2 to map an image, a sounding image to a nighttime image through adversarial training. Adversarial training will make sure the output image is a nighttime image, but not necessarily correspond to the translation of daytime images. We need something more. So what we do is to apply weight sharing constraints to limit the network capacity. We share the high-level weights of E1 and E2 as well as G1, G2. So this creates an information bottleneck and encourage the generated images, a translated version of the input image. So this is a couple-GAN framework, and we build our image translation model based on this framework. So I'm going to show you some results. We applied our model to different image translation tasks. Here are some examples where we translate a daytime image to a nighttime image, where we turn on the lights of the cars. Another example is translating a wintertime image to summertime image, where we remove the snow and add the leaves back to the trees. For sunny to rainy translation, we add the raindrops and make the ground wet, and you can see the reflection. And we also test on translating real images to synthetic images. We have both way translations. We also tested on translate image animal profiles. Here is the translation between different species of cats. Given an input house cat images, we can translate to a cougar, to a cheetah, to a leopard, to a lion, to a tiger. So the translated image looks realistic and roughly in the same pose of the input images. So if you want to make your house cat more fierce, we can help. So the conclusion is we propose a coupled GAN framework for unsupervised image-to-image translation. We achieve it by introducing the shared latent space assumption with adversarial training. And the code and the results are available in the website, and the poster number is 120. Thank you.
So hi, I'm Lars Mescheder from the Max Planck Institute for Intelligent Systems in Turing, and I would like to present our work on the numerics of generative adversarial networks, which is joint work with my supervisors, Sebastian Novotny and Andreas Geiger. So why are GANs difficult to train? To answer this question, we performed a local analysis based on the following simple observation. While local optimization can be understood as applying Euler's method to a rotation-free vector field like the one shown on the left, GAN optimization can be understood as applying Euler's method to a vector field with a strong rotational component like the one shown on the right. More formally, GANs are usually trained using an algorithm called simultaneous gradient descent. As the name says, simultaneous gradient descent simply computes and applies the gradients for the generator and discriminator simultaneously. Based on our insights, we also introduced an alternative optimization scheme which makes GAN optimization provably more stable in a local neighborhood of the Nash equilibrium. Our paper is part of the growing body of work on the stability properties of GAN training, while other works have considered the case of step sizes that eventually go to zero and show convergence under certain strong regularity assumptions. We consider the case of a fixed finite step size. As it turns out, this leads to additional insights on the stability properties of GAN training that cannot be obtained by only looking at step sizes that go to zero. In our paper, we derive geometric and algebraic conditions that ensure local convergence of GAN training. More specifically, we show that GANs are locally convergent to a Nash equilibrium if all eigenvalues of the Jacobian of the gradient vector field at the equilibrium point can be projected into the unit ball along rays starting at 1. So while in this example here, GAN training is divergent for h equals 1.0 and h equals 0.7, it is locally convergent for h equals 0.4. Formally, this leads to a condition on the step size as shown on the slide. To see what can go wrong, we measured the eigenvalue distribution for a simple real-world problem where simultaneous gradient descent fails. As you can see in the plot on the left-hand side, the Jacobian has eigenvalues close to the imaginary axis, which cannot be easily projected into the unit ball unless we use extremely small step sizes, and it is in fact impossible if the eigenvalues are on the imaginary axis. To alleviate this problem, we introduce a simple regularization term that moves the eigenvalues to the left, making it easier to project them into the unit ball. While our algorithm can, in practice, introduce new spurious attractors to the GAN training dynamics, we empirically found that in many cases, our algorithm does successfully stabilize GAN training. For example, while alternating gradient ascent does not work well for a deep convolutional GAN with the constant number of filters in each layer, no batch normalization, and additional resonant layers, we found that our algorithm trains this architecture successfully. We hope that our work sheds some light on the training instabilities that practitioners often encounter when training GANs, and we believe that our work paves the way for future training algorithms for GANs as well as further theoretical studies on the training properties. Thanks for your attention. If you're interested or have questions, please drop by at our poster.
Hi everyone, I'm Tu. So today I would like to talk about our paper, the two-GAN dual discriminator generative adversarial nets. So we all know that GAN is a powerful generative model that can generate sharp and realistic images. And basically, GAN formulates a game between two players, a generator that can map from the noise sample from prior distribution to the input data space, and a discriminator acts as classifier to distinguish the real sample from training data and fake sample generated by the generator. And we can train GAN by alternatively update the generator and discriminator via the minimax objective function. But GAN has a fundamental problem, that is, the objective function of GANs try to find the generator to minimize the gensensonal divergence between the data and the model distribution. This is more similar to minimizing the reverse KL divergence than the KL divergence. And it has been pointed out that minimizing the reverse KL divergence lead to mode collapsing problem, where the model can only capture a single mode and produce the similar samples. And at the same time, minimizing the KL diversion tends to cover all data modes. So we come up with a solution that we combine both two diversion, the reverse KL diversion and the KL diversion, in a unified objective function that we can exploit the complementary statistical strength of these two diversions. And we introduce one more discriminator to the standard GAN to formulate a game between three players. A discriminator T1 that rewards high score for sample generated from data distribution, and by contrast, another discriminator D1, D2 reward high score for the data from model distribution, and the last one is a generator that creates data to fool both two discriminator. And similar to GAN, we can train our D2 GAN by alternatively minimizing the generator and maximizing both two discriminator. We also provide the theoretical analysis for our model that I skipped the detail here, but basically we can prove that at the optimal point, the training result in the minimal distance between the data and model distribution with respect to the both reverse KL and KL diversion, and hence our model can effectively overcome the mode collapsing problem. And we point out some correlation between our model and f-GAN. Using appropriate activation function and the conjugate function, we can recover the minimization of KL and reverse KL diversion in our model. But f-GAN only consider a single diversion, while our model consider the combination of two diversions. We conduct experiments on synthetic and real-world data set. On synthetic 2D data, we show the improvement on covering the mixture of 8 Gaussian components and with better symmetric KL and worse sustained distance. For real-world data set, we first compute the mode score on MNIPS and MNIPS 1K data set. We also study the effect of hyperparameters alpha and beta on the model performance. Here are some generated samples for MNIPS 1K data set. And the last experiment, we compare the inception score of our model with up-to-date GAN baselines for natural scene images dataset, that is CFAT10, SDL10, and ImageNet. We see that our models cannot compete with denoising feature matching DFA model, but outperform the other baseline by a large margin. And these are some generated images from the natural scene data by our model. Some reference for our spotlight presentation. And finally, we would like to acknowledge the ARC Discovery Grant for funding. Thank you all for your attention, and welcome to our poster this evening. Thank you.
Hi everyone, I'm Eunice. And I'm Andrew, and we're going to give a short presentation on the Bayesian GAN. So in generative adversarial networks, a generator G proposes samples from a data distribution, attempting to fool a discriminator D as part of an adversarial game. The exact minimax training objective is shown in blue. In the original paper by Goodfellow et al., they present an analogy whereby a gang is trying to produce counterfeit currency to fool the police. The police get better at calling out the fakes, and the gang gets better at producing counterfeits, until eventually it's generating actual currency. GANs are particularly good at learning to sample from a distribution over images, leveraging both the capacity and inductive biases of deep convolutional neural networks. Here we show sample celebrity faces from a recent GAN model proposed by Karas et al. Each of these faces is entirely fictional, yet quite realistic. However, GANs typically suffer from stability issues. Mode collapse is a common issue whereby the generator collapses most of its mass onto just a few training examples. Mode collapse is reminiscent of overfitting when we do maximum likelihood density estimation with mixtures of Gaussians, and the Gaussian components collapse all of their mass onto individual points, memorizing the training set. In the analogy, we can imagine that the gang produces a good $5 bill and the police are quite convinced. The gang then learns to only produce $5 bills, making the police happy, but not sampling from a full distribution over currency. We can see in these generated images of flowers there isn't a lot of diversity. We can also see in the next row that the generator, as it proceeds through training, is sampling from different modes of a multimodal distribution, but in any given iteration, it's not capturing the full multimodal distribution. Fixing these stability issues typically involves a lot of intervention, such as mini-batch discrimination, feature matching, and label smoothing. In this paper, we propose a Bayesian GAN, which introduces distributions over the generator and discriminator. The generator can now be viewed as a distribution over distributions. The proposed likelihood is inspired by using the discriminator as a link function, much like how a logistic sigmoid is chosen as a link function in logistic regression. Moreover, this approach is a natural Bayesian generalization of the classical GAN. If we use vague priors over the generator and discriminator parameters and perform map optimization, then we recover the classical GAN. In the figure on the right, top panel, we have images produced by 6 different generators sampled from our posterior over generators. In the bottom row, we have 6 DC GANs, which are generating images, and they've been trained independently. Generators sampled from the posterior represent different generative hypotheses for the data, corresponding to different qualitative properties, such as different writing styles and writing utensils. Samples from the DC GAN, by contrast, are relatively homogeneous in style. Now, Eunice is going to tell us about the experiments.
Thanks, Andrew. So in this synthetic data set, we can clearly capture the mode collapse phenomenon for a regular GAN. And we can also see that the Bayesian GAN completely avoids this mode collapse issue, right, without resorting to the ad hoc interventions that Andrew mentioned in the earlier slides, which is great. So in addition to actually sampling from a multimodal distribution properly, the GAN also has, we can show that it has a multimodal posterior. So you can see that at the bottom right plot. And because it's basically modeling the data generating distribution much better, because it's multimodal, right? It actually does a much better job at optimizing the Jensen-Shannon divergence, which you see on the top right, which is very promising. We also ran so an excellent way to actually measure the generative power of GANs is actually via the method of semi-supervised learning. And we find the Bayesian GAN to be particularly effective at that. It actually has better test accuracy compared to the maximum likelihood / vanilla DC GAN across a range of different benchmark data sets and for any given number of label samples. In fact, we observed that with the Bayesian GAN, we can achieve close to state-of-the-art results with a mere 1% of the labels. And the rest of the data comes obviously unlabeled. So that's very promising as a result. In future work, we want to try out deterministic approximate inference, like variational methods. We're using HMC in this paper. We try out different architectures, different priors, like sparsity-inducing priors for the GAN and new applications. The code is available on GitHub. You can check it out. And if you have any more questions, please come to our poster. It's number 112. We look forward to chatting with you. Thanks.
Hello, everyone. Today I'm going to talk about approximation and convergence properties of generative adversarial learning. So I'm Shuang Liu. This is a joint work with Olivia Busquets from Google and my advisor, Kamalika Chaudhry. So first, let's just briefly review what GAN is doing. So you're given a data set, in this case, the MNIST data set. You want to learn a generative model that can generate MNIST digits. So the way GANs do it is to have a generator that transforms the noise, which in this case is the Gaussian noise, into MNIST images. So we can say that at first, generator may only be capable of generating blurry, if not totally unreal images. But the generator can improve itself through a discriminator, which during the training tells whether the generated data and the true data are actually from the same distribution. So the generator keeps improving itself until the discriminator can no longer distinguish the two data distributions anymore. So despite GAN's empirical success, there are many fundamental questions that remain unanswered. So in our work, we address two of them. First one, we really want to know what the goal or what the role of the discriminator is in GANs. So we want to know, for example, what if the discriminator has very limited capacity? What if it's essentially only capable of doing, say, linear regressions in some feature space? The second question is, for GANs, we usually have this value of the two-player game that we want to achieve. So we want to know if the objective function converges to the value of the game. Does this imply that the generated data set is also converging to the true data set? So for the first question, we show that the discriminator, if the discriminator has very limited capacity, we show that most of the existing GANs are actually doing generalized moment matching. For example, if we have this phi of x that transforms data points x into some points in the feature space, then the optimum of the objective function is achieved if and only if the expectation of phi of x over the true data set is equal to the expectation over the generated data set. So for the second question, we show that the answer is yes. More specifically, we show that the generated distribution weakly converges to the true distribution as long as the following two assumptions are met. The first one is the domain of the data should come from a compact metric space. So for example, a bounded subset of a Euclidean space is a compact metric space. So we can see that real-world data sets usually fit into this regime. So the second condition is the discriminator should use only continuous functions. For example, in neural networks, we use two types of functions. The first one is linear transformations, which are definitely continuous. The second one is activation functions, which almost all of them are continuous. So if you're interested in our work, please come to our poster so we can discuss more about it. Thank you so much for your attention.
Okay, my name is Yu Jia. I'm presenting Dueling GANs, which is a joint work with my collaborators from University of Toronto, Vector Institute, and University of Illinois. So GANs, generative adversarial networks, are typically formulated as a problem of finding the saddle point for some loss function, where the discriminator minimizes its loss over its parameters w, and the generator maximizes its loss over its parameter theta. And typically, learning is done by alternating gradient updates for the generator parameters and discriminator parameters. This, unfortunately, typically leads to instability. In this paper, we propose to convert the inner optimization problem for the discriminator into its dual form, which maximizes the dual objective G over its dual parameters lambda, and convert the max-min problem into max-max, which is much more stable. Let's take a look at GANs with linear discriminators to start with. So here the discriminator uses a linear scoring function, and we pass the score through a sigmoid to get probabilities. The GAN loss looks like the following, which is basically the standard classification loss plus an extra L2 normalizer. Here, the discriminator has a problem of binary classification, where it tries to tell apart real images from generated images. And this loss has a nice property that it is convex in discriminator parameters W, and we can therefore easily convert it into its dual form through a procedure that's pretty common in, for example, SVMs. And if you look at the dual objective, then it contains two parts. The first part is the square term, which encourages moment matching. And the second part is the entropy term, which encourages the dual variables to be not too extreme. And we also have a bunch of bound constraints in this dual problem. Learning can be done by alternating gradient updates to the generator parameter and solving the dual for the discriminator. Empirically, solving the dual is actually not that hard because it's a small-scale quadratic optimization problem, and we can call a QP solver to solve it to a good accuracy. Note that typically in standard GANs, you do one or a few gradient updates for the discriminator, while here we can actually solve for the optimal discriminator. Learning is very stable compared to standard GANs. Here we're showing typical training curves comparing dual GANs and standard GANs, training the same generator and using the same discriminator. On the x-axis, you see is the number of training iterations, and we're plotting a few different metrics, including primal objective, dual objective, and discriminator accuracy. You can see that with the dual GAN, the training curve is almost monotonic and very stable, while the standard GAN suffers from instability even with the linear discriminator. We also tackled nonlinear discriminators, but the problem with that, it is a bit more challenging. In the paper, we proposed two approaches to handle nonlinear discriminators, and empirical results show that our dual GANs are typically more stable than standard GANs, while achieving the same level of sample quality. If you want to know more, please come to our poster tonight at number 103. Thank you for your attention.
Hi there, this is Roderick Rose, and I'm presenting work together with you, Yui Gu, Wei Li, and Melvin Gauci on generalizing GANs. Recently, a new family of machine learning algorithms have emerged that are not just trying to build models that are similar to a certain system, but that are indistinguishable. And this includes our work on model discriminator evolution as co-evolution, as well as more recently the work on generative adversarial networks. All of these algorithms have in common that they relate to the famous Turing test. But there could be many more of these algorithms that are kind of going along the same spirit, and this is what kind of this talk is about. So to give a small recap, the Turing test probes a machine's ability to display behavior that to an interrogator is indistinguishable to that from a human. Here, player A is a machine, player B the human, and player C this interrogator. For GANs and variants, player C is trained to discriminate between players A and B, whereas player A is trained to fool the interrogator. And player B can be any system you wish to imitate, including humans. Now, when you take this Turing perspective and look at GANs, you can kind of extract the features that are core to the idea, which we call the defining features, and all the rest we consider as kind of an implementation detail that is depends on the application that you have in mind or personal preference. So the defining features are that there is a training and a model agent that produce data samples, that there is a discriminator agent that is labeling these samples, and there's a process by which the discriminator can observe or interact with the other agents. Moreover, there is an optimization process by which the discriminators are rewarded for labeling correctly, and the models are rewarded for misleading the discriminator. Now, when it comes to implementation to GANs, there's lots of choices. So we have used co-evolutionary algorithms. We have heard, in GANs, gradient descent is currently being used. And I'm not saying that one is better than the other, but my point is that probably the very best implementations are yet to be discovered by some of you, and there's a lot of options. So all of the algorithms that have these defining features, including those that haven't been discovered, we call Turing learning, which is a generalization of GANs. Model representations, other than generative networks, can be considered. So if you're interested, you can look at vectors, graphs, or computer programs. In terms of optimization algorithms, I know that people in this room know at NIPS there is no free lunch, and this is kind of also generally true. But yet a lot of people know that for specific applications, some optimization algorithms are better than others. So why not watch out for them? Now we are presenting also some case studies in the paper, and the point of these case studies is to show why, one particular generalization, and this is that the discriminator is no longer just passively observing some data. So in our case study, we have a robot that tries to find out where its sensors are located while moving around in an environment with obstacles. I'm just restarting this video. You can see it again. And the robot starts from a random position in the environment, so it doesn't know where are the obstacles, and it doesn't know where are the sensors to sense these obstacles. So that's a chicken and egg problem. And Turing learning is able to solve this problem, but only if the discriminator is allowed to control the movements of the robot in real time while getting the sensor readings from it. So it's doing closed loop control. And this, as you can see here in the red boxes, brings about the parameter values that we estimate that are close to the ground truth, that is the physical locations on the physical robot. Whereas if you use the discriminator to observe the sensor readings while the robot is moving around at random, so not being controlled, then you get really terrible performance, as you can see here with the green and blue boxes. So to sum up, we have proposed a generalized framework that we call Turing learning, which is not just about generative models, but can be really anything, any sort of model representation you're interested in. It could be even physical objects if you want. And in the second part of the talk, we talk about discriminators that interrogate, that is, that define in real time the conditions under which the process is to be observed. And we show that through this interrogative, interactive process, the model accuracy can be improved for certain problems. And this is certainly true if you want to learn about humans, because humans have an internal state, the environment has a state, how they react depends on the state, and so forth. So perhaps one day we get machines that can pass the Turing test. Thank you very much.
Okay, that concludes the session. Thanks for attending.